to present for the first time in public our open source blockchain code, which by the time that you're watching this should already be available on our GitHub.
Thank you, Stefan. So I'm going to be presenting the code for the blockchain. The blockchain is built with Substrate. We have two palettes, main palettes that we'll be showing, which are our custom palettes. One is the schemas palette and the other is the credentials palette. The credentials palette is tightly coupled to the schemas palette. So I'll first start with the schemas palette in my presentation. So we have the usual defaults for creating any palette, the config, the firm config for the schemas palette, which will give us the parameters and types the palette depends on. Then we have the schema store, that is the storage parameters. We also have the events that are emitted, which are, since this is mostly accrued palette, these are just create, update, and delete. Then we also have the error messages that are emitted. So I'll start with the main functions. So the main functions are the create functions, create, delete, and update. These are tied to a trait that we created. So this trait basically implements these functions in the lib.rs. So I'll start with the create function. The create function basically takes in an origin. So we cross-check that we first of all split the public key from the submitted creator. Then we check that the creator that you are submitting is the same as the origin. So what the origin does is it represents it's the account that sends an extrinsic when you're submitting it. So we ensure that the creator is the same as the origin. If it is not, when we emit an error. This is not the schema owner. If it is, we check. Then we go into another check where we check that the schema that you are submitting, the ID, doesn't already exist. Once we validate that it doesn't already exist, we then submit this to the create verifiable schema function. The create verifiable schema function is, we shall look at it below in the implementation of the schema trait. We also have the update function. So as you have noticed, all these functions have their weights. So these were already generated. The weights are basically going to be used when determining the fees for each extrinsic call. So the update schema takes in the schema ID of the schema that you want to update, which is the old schema key, and then the schema data. So whenever you update a schema, you have to submit a new signature. The schema update also takes in an origin, which I had already explained earlier. So once you submit the schema key, we fetch that schema. Then once we fetch that schema, we validate that that schema actually exists, the schema that you're trying to update. After validating it exists, we then check if the schema creator and the origin are the same. This is to make sure not the person that updates the schema is actually the owner of that schema. So if you're not, it will give you that same error that you're not the schema owner. Once we do that, we check that the schema that you are submitting is not the same as the new schema. So if all those validations are checked, then we submit the schema to be updated. Then we also have the delete schema function. The delete schema function also takes in an origin. This is, by the way, a default on most substrate palettes. Actually, on all, you have to you have to ensure that the extrinsic is signed. It's possible to submit an unsigned extrinsic, but in our case, we ensure that the extrinsic is signed because we want to validate the sign of that extrinsic. We fetch that schema that you want to delete. So you submit a schema ID. We use that schema ID to fetch the schema that you want to delete. Then we check the schema creator. So this split public key from DID is because when you submit a DID, the DID basically contains an account ID, and we need that account ID to be the same as that of the schema creator. As I explained earlier, we don't want someone who is not the schema creator or an account that is not the schema creator to be able to delete or update any data from the chain. Then we have the implementation of the schema trait. So it has a couple of generics. It takes in a generic of account ID, the moment, the signature, and schema ID. These are used in all the functions. So the create verifiable schema function basically takes in all the components that the components that are used for creating a verifiable schema. These are used to create a struct for that verifiable schema. And then we encode that into a vec of U8s, basically a vec of bytes. Then we take a slice of those bytes, and that slice is what is going to be validated when verifying the signature. So as you can see here, we validate the signer. So we are validating the signature and the signer. We get the signer. The signer is that account ID of the creator. So we do again the same thing. We split the public key from the DID. Then we insert that particular schema into the schema store. And then finally emit an event with the schema ID and the schema itself that has been submitted. So we also go with we go into updating a schema. This updating of the schema takes in the schema ID, the old schema ID, as I mentioned earlier, and the new data that is being submitted. So we insert that because all the checks on this function, all the checks have happened in the previous function above here. We don't have any more additional checks. So when we come here, we just submit that particular schema and then emit an event. So these are not public functions. The public functions are above here, the ones that have all the checks. In the implementation of the trait, these are all private functions. So this is done so that no one can just override these functions and submit something without the checks that are needed. The same thing happens in the delete schema verifiable schema function. We just take in the key, which is the schema ID, and remove that particular schema from the schema store. Then we also validate the signer. Is signer valid, which I had showed above. This just ensures that the signature is verifiable. So we just take the data and the signature and validate that that data is correct. Sorry, we take the data and the account and the account ID, and we use that for verifying the signature. Most of this is SR 25519 signature that we are verifying, and also we use SR 25519 for signing. We are not supporting multi-signer yet, but in the future we will. Then for the public, this function that splits the public key from the DID, it just takes in the DID and we use a function that basically splits this DID and returns it as a string. And once we return that DID as a string, we split that DID from the DID prefix from the account ID, and then finally we convert it to one account ID. So there's also this schema interface. There's a trait for the schema interface defined here. This schema interface trait is mostly used in credentials. So I'll explain it more when we get into the credentials into the credentials palette. But what we do is just check if the schema ID exists, and also convert a U32 into a schema ID. So let me go into the credentials palette. So our credentials palette has the same mechanism, except that it's tightly coupled to the schemas palette. So some of the things or the types that we are using in this palette are coming from the schemas palette. That is like the moment types, where we are basically depending on some types that are defined in the schemas palette. So we have the same mechanism. We have the credential store. We also emit events, and also have the errors. So I'll go into the functions. For this, I'll be pretty fast because most of what we're doing is already the same as what we were doing in the schemas. So we have an origin that has created we have an origin that has created the schemas palette. Sorry, the credentials palette. The origin is basically the issuer. It should be the same as the issuer, and we check for that here. We also get the schema. We check for the schema ID so that you're not submitting a credential for a non-existent schema. The schema should exist that you're submitting the credential for. Finally, we call a function that is defined. We have a trait here, credentials trait. It defines functions that we are going to use. So some of these are going to be what we submit these credentials to. Then the update credential just takes in the old credential key and the new credential you want to submit. As I said, whenever you're submitting new credentials or new schemas, you have to sign them again. So as you submit that, we go into a check. We check that the credential you're submitting actually exists. So if you are submitting a credential that doesn't exist, it will emit that error. Then finally, we check that the credential creator or the issuer is actually the same as the origin, so that whoever is making this update isn't a ghost. We don't want to have updates that we can't recognize who has made that update. Then for delete credentials, we just take in our credential key, and that key is used to validate that the credential we want to delete exists. Then we check that the credential creator is the one deleting that credential. And finally, we delete the credential. So similar things happen here, like were happening in the schemas palette. We implement the credential trait. Then we implement the functions, create credential, creates a struct. Then we encode that struct into a vector of bytes. Then we create a struct. We create a slice from. We do a conversion and create a slice from that vector of bytes. And finally, we get the signer and validate the signature. Then finally insert that credential into the credential store. For update, the checks had already happened up there. So we just insert the update and emit an event. And the same thing for delete verifiable credential. We take in the key and just call the credential store function that is remove that particular credential and emit a message that shows that this particular credential has been deleted. Yeah, so that's it. Most of these functions are the same. Get schema by schema ID. These are just registry functions to allow you to easily fetch this data. So get schema by schema ID does exactly what it says. Get credential by schema ID. You would basically get all credentials that belong to that schema. Get credentials by subject. You would be able to get all credentials that's particular subject. Get credentials by holder. You would be able to get all credentials that particular holder holds. Then get credentials by creator. You would be able to get all credentials that were issued by that particular issuer. Yeah, thank you very much for your time.
No, this is awesome. I mean, we went over a lot of code, but credentials and schemas are super important to our implementation on Seneca. So if you haven't worked with verifiable credentials before, they're basically what allows us to exchange user-owned data between different devices in the zero-knowledge environments. And it allows us to verify data by third parties and then use that information within smart contracts. And even more important, we are probably one of the very few blockchains who took the verifiable credentials standard and extended it to add schemas that act as data exchange mechanism or data structures that multiple parties can use with each other and depend on the same data structures between each other. So I think this is absolutely awesome. Thank you for the walkthrough to Mukunda. I think it will come useful to the people who will check out our open source blockchain code on our GitHub.
Awesome. Thank you, Stefan. Thank you, guys. Really exciting updates. Just as a reminder, we do this call every Thursday at 12 Eastern. And please engage with us on Discord. If you're watching this video, you're going to be on some type of medium where you can find our Discord link. If not, go to seneca.tech. We really want to hear from you and support you as you build. So thanks again to everybody. Have a good week, and we'll see you next week at this time. Thank you.